For over 4.5 decades, Voyager 1 has traveled a singular path, moving away from the Sun, away from Earth, and leaving behind everything familiar. It stands as the furthest human-made object in existence, drifting over 14 billion miles from home, whispering data back to Earth using technology older than a cassette deck, fueled by a dying nuclear heart designed in the 1970s. Yet, at the very edge of the solar system, a strange event occurred. Voyager 1 didn't physically reverse course. However, the data it returned forced scientists to reverse their assumptions, because what it discovered beyond our solar boundary did not behave the way any model predicted. The border wasn't where it was supposed to be. The magnetic fields didn't shift the way they were expected to. And the protective bubble we thought surrounded us proved to be far more baffling, and potentially far more fragile, than we ever conceived. Voyager 1 confirmed something we were never quite ready to face. Interstellar space was never Voyager 1's intended destination. Its mission was originally slated to last just 4 years, long enough to fly past Jupiter and Saturn and transmit images that would have been considered historic in their own right. Instead, it evolved into something entirely different. Launching in 1977, Voyager 1 capitalized on a rare planetary alignment that happens only once every 176 years. It was a cosmic coincidence that allowed it to use gravity itself as a propulsion system, stealing velocity from massive planets like Jupiter and Saturn as if towed by invisible lines. That maneuver compressed a 30-year trek into just 12, launching Voyager onto a trajectory no spacecraft had ever traveled before. Decades later, defying every expectation, Voyager 1 was still alive, still broadcasting, and still rewriting the textbooks. By the time it neared the edge of the heliosphere, the vast bubble formed by the Sun's solar wind, scientists thought they knew exactly what was coming next. They were mistaken. The heliopause is meant to be simple. It is the boundary where the Sun's reach ends and interstellar space begins. A clear line dividing two environments governed by different forces. Voyager 1 hit that boundary in August 2012. Theoretically, the moment it crossed into interstellar space, several things should have occurred simultaneously. Galactic cosmic rays should have spiked dramatically. Plasma density should have risen. Most crucially, the direction of the magnetic field should have shifted, moving from the Sun's influence to that of nearby stars. Some of that did happen. Cosmic rays increased. Plasma density rose. But the magnetic field refused to comply. Its direction remained almost perfectly aligned with the Sun's field, a phenomenon no existing model could fully explain. It was as if Voyager had crossed a physical border, but not a magnetic one. This raised a disturbing question. Had Voyager 1 truly left the solar system, or were our definitions of outside completely wrong? We have long imagined the heliosphere as a protective cocoon, a magnetic shield defending the inner solar system from the galaxy's harsh environment. Voyager 1 complicated that picture. As it moved further outward, its instruments picked up small-scale turbulence near the heliopause, regions where solar and interstellar forces clashed in unpredictable ways. Yet, on larger scales, the magnetic environment remained strangely uniform. This contradicted simulations that predicted dramatic structural changes driven by the Sun's 11-year activity cycle. When Voyager 2 crossed the heliopause in 2018, the solar wind was at its peak, meaning the boundary should have been pushed further outward. It wasn't. Both Voyagers crossed at roughly the same distance, about 120 astronomical units. This result made scientists wonder if the heliosphere behaves as a dynamic shield at all, or if it is something far more complex and poorly understood. Voyager 1 didn't turn back physically, but it forced science to turn back conceptually. What makes this narrative even more striking is that Voyager 1 continues to function at all. It operates on less energy than a household light bulb. Its computers possess just 69 kilobytes of memory. Its data is saved on 8-track tape recorders, and its radio signal, transmitted by a 23-watt antenna, takes over 22 hours to reach Earth. As its plutonium power source slowly decays, NASA engineers have adopted a triage strategy, shutting down heaters and instruments one by one. In one astonishing instance, a cosmic ray detector kept operating even after its heater was cut, surviving temperatures far lower than anything it was ever tested for. Voyager 1 is now expected to keep transmitting data into the late 2020s, perhaps until around 2030. After that, silence will fall, but motion will not cease. In roughly 16,700 years, Voyager 1 will pass near Proxima Centauri. Long after Earth has changed, long after the heliosphere itself has vanished, Voyager 1 will still be there. One of the most uncomfortable implications of Voyager 1's data is that the solar system may not be as isolated from the galaxy as we once believed. For decades, the heliosphere was described as a robust barrier, a cosmic firewall separating us from the dangerous environment beyond. Voyager 1 suggests this barrier is neither uniform nor impermeable. Measurements taken after crossing the heliopause revealed that galactic cosmic rays penetrate the boundary far more efficiently than expected. These high-energy particles don't simply bounce off the heliosphere. They leak through it, and they do so constantly. This means the solar system exists in a state of ongoing interaction with interstellar space, not separation from it. The sun's influence fades, but it never fully blocks what lies beyond. Our planetary neighborhood isn't sealed. It is porous. Voyager 1 didn't just leave the solar system. It revealed that the solar system was never fully closed to begin with. Another deeply unsettling discovery is that the heliopause is not fixed. It isn't a stable shell with a clearly defined edge. It moves. Voyager 1 detected fluctuations in plasma density and pressure, suggesting the boundary shifts inward and outward depending on conditions in interstellar space. Shock waves from distant supernovae, changes in the local interstellar medium, and variations in galactic magnetic fields can all dictate where that boundary sits. This means the size of our protective bubble can shrink. At certain moments in cosmic history, the heliosphere may have been significantly smaller than it is today. During those periods, Earth and the inner planets would have been exposed to much higher levels of radiation. Voyager 1 confirmed that our cosmic environment is not constant. It evolves, and sometimes it becomes more dangerous. One of the strangest aspects of Voyager 1's journey is what it didn't find. Scientists expected interstellar space to be chaotic, turbulent, and noisy. Instead, Voyager detected an eerie uniformity in the plasma waves beyond the heliopause, a steady hum, a persistent background vibration. This signal is now understood as the oscillation of interstellar plasma itself. But its stability raised eyebrows in a region shaped by ancient supernovae and galactic forces. Such consistency was unexpected. It suggests that interstellar space, at least locally, is more structured and ordered than previously assumed. Not empty, not random, but governed by large-scale processes that operate quietly over immense timescales. Voyager 1 revealed that the void between stars is not chaos. It is a system. Perhaps the most haunting aspect of Voyager 1's mission is not what it discovered, but what it represents. Voyager 1 carries no propulsion to return. No course corrections can lead it home, and there is no possibility of rescue or retrieval. Every bit of data it sends is a one-way transmission, a final report from a place humanity cannot yet reach. As its power fades, each signal becomes more precious. Each measurement is irreplaceable. Once Voyager 1 goes silent, that voice from interstellar space is gone forever. What it leaves behind is not just data, but confirmation. Confirmation that our place in the universe is more fragile than we assumed. That our cosmic shelter is thinner, more dynamic, and more vulnerable than the models once suggested. Voyager 1 didn't turn back, but it sent back a warning we cannot ignore. For decades, heliophysics relied on elegant simulations. Equations that balanced solar wind pressure against interstellar pressure, boundaries that behaved predictably, a shield that expanded and contracted in neat cycles. Voyager 1 shattered that comfort. This forced scientists into an uncomfortable position. Either the models were missing critical variables, or the underlying assumptions were flawed from the start. In science, that moment is dangerous. It means progress requires dismantling what once felt solid. Voyager 1 didn't just add data. It destabilized confidence. Another realization emerging from Voyager 1's measurements is that the galaxy is not a passive backdrop. It is an active environment with its own weather. Interstellar space contains shock fronts, pressure gradients, and magnetic structures shaped by ancient supernovae. Voyager's instruments suggest our solar system is currently traveling through a relatively calm region of that environment. But calm is temporary. As the Sun orbits the Milky Way, it inevitably passes through denser clouds and more turbulent regions. In those moments, the heliosphere could be compressed dramatically, exposing the inner planets to increased radiation for thousands of years at a time. Voyager 1 confirms that cosmic safety is situational, not permanent. Looking backward through geological records on Earth, scientists have long debated whether spikes in radiation may have influenced climate shifts or biological stress events. Voyager 1 gives that debate new context. If the heliosphere can shrink and swell based on galactic conditions, then Earth's radiation environment may have changed significantly across deep time, not randomly, but cyclically, tied to the Sun's journey through the galaxy. Voyager 1 does not prove this directly, but it makes it plausible. It turns radiation exposure from a hypothetical threat into a variable that must be considered when studying Earth's long-term habitability. The fear Voyager confirms is not sudden catastrophe. It is slow vulnerability. Perhaps the most unsettling implication of all is what Voyager 1 implies about civilizations in general. If a star's protective bubble is essential for long-term habitability, then intelligent life may depend not only on planets and chemistry, but on galactic positioning and timing. Civilizations could rise during calm epochs and vanish during harsher ones, not because of self-destruction, but because their cosmic shelter weakened. Voyager 1 quietly suggests that survival may depend on where and when a civilization exists within the galaxy. That reframes the question of rarity. Maybe life is not rare. Maybe stable cosmic conditions are. One of the most disturbing ideas emerging from Voyager 1's data is that the heliosphere may not be a permanent feature at all. It exists because the Sun generates a strong enough solar wind to push back the interstellar medium. But that balance is delicate. Stars age, solar output changes, galactic environments evolve. Voyager 1 reminds us that the heliosphere is not a fundamental law of nature. It is an emergent structure, the temporary result of competing pressures. Change those pressures, and the structure changes with them. In other words, our cosmic shelter is not guaranteed by physics. It is maintained by circumstance. Voyager 1 didn't just explore space. It exposed how provisional our protection really is. The Sun is not stationary. It orbits the center of the Milky Way once every 225 million years, traveling through regions of space with radically different densities, magnetic properties, and radiation environments. Voyager 1's measurements make it clear that interstellar space is not uniform. Some regions are calm, others are dense and turbulent, and the solar system will inevitably pass through all of them. When it does, the heliosphere will respond. It may shrink. It may distort. It may allow more cosmic radiation to reach the inner planets, not as a sudden disaster, but as a slow, persistent change that could last for millennia. Voyager 1 confirms that the solar system is not isolated from the galaxy's long-term evolution. It is embedded within it. Voyager 1 also forces a humbling comparison between human technology and cosmic timescales. This spacecraft represents one of humanity's greatest engineering achievements. And yet, it is powerless to adjust its fate. No propulsion, no repairs, no updates, just motion. Its journey highlights a hard truth. Once we leave the solar system, our machines are entirely at the mercy of galactic conditions we barely understand, let alone control. Interstellar travel is not just a technological challenge. It is an environmental one, a journey through regions shaped by forces operating on scales far beyond any human intervention. Voyager 1 didn't fail. It revealed how small our reach still is. Perhaps the most unsettling aspect of Voyager 1's legacy is the timing. We now know far more about the heliosphere, cosmic radiation, and interstellar space than ever before. But knowledge does not equal readiness. We understand the risks long before we have the means to mitigate them. Voyager 1 has given us warnings centuries ahead of our ability to respond. It shows us vulnerabilities we cannot yet shield against and environments we cannot yet navigate safely. This creates a strange paradox. We are learning about dangers long before we are capable of facing them. Voyager 1 confirms what we feared, not because it predicts doom, but because it shows how early we still are in our cosmic story. Voyager 1 did not turn back, because it hit a wall. It turned us back because it revealed a truth we had been avoiding. For decades, we believed the solar system was safely wrapped inside a stable, protective bubble, a kind of cosmic home, quietly drifting through the galaxy, shielded from the worst of what lies beyond. Voyager 1 showed us that this belief was comforting, but incomplete. The boundary is thinner than we thought. The shield is more dynamic than we assumed, and the galaxy around us is not neutral. Voyager 1 confirmed that our safety depends on balance, on pressure, on timing, on where the sun happens to be as it moves through a changing Milky Way. Our protection is not guaranteed by the universe. It is negotiated moment by moment. That is what we feared. Not invasion, not aliens, not sudden catastrophe, but vulnerability. The realization that life on Earth exists inside a temporary pocket of calm shaped by forces far larger than our planet, far larger than our species, and far beyond our control. Voyager 1 did not bring back panic. It brought perspective. And that perspective matters because, for the first time, humanity is not guessing about what lies beyond our cosmic doorstep. We have measurements. We have data. We have proof. And that proof tells us we are early in our journey, protected for now, but not forever. Voyager 1 will go silent. Soon its voice will fade into the background of the universe. But the message it sent back will remain. A reminder that exploration is not about comfort. It is about truth. We are not fragile because the universe is dangerous. We are fragile because we are part of it. And if this story made you look at the night sky differently, stay with us. Subscribe, because the more we explore, the more we realize that understanding the universe is not about conquering it, but about learning how to survive within it. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.